Okay. Um, so welcome everyone to the Rubin Science Assembly. I'm Jeff Carlin. I'm sure many of you recognize me. Um, and I will be talking to you today about how to inject synthetic sources into the Rubin data products. So I'll have just a couple of announcements and then we'll just get right into the fun stuff. A reminder that the tutorial notebooks are automatically preloaded into your science platform space. But if you want to download them directly, you can go to the tutorial notebooks repository on GitHub. And yeah, announcements. If you didn't see it, I encourage folks to check out the press release that came out earlier, or last week, I guess. There is a video about, let's see, about a 2-minute video telling you all about the LSST camera and its journey from the lab at SLAC in Northern California to the mountaintop in Chile. So the camera is now on the mountaintop being checked out and prepared to be placed on the telescope in a few months. A reminder also that if you're interested, the Rubin Community Workshop is coming up in July, also at SLAC in Northern California. And there is a virtual component if you're interested. Registration is still open, and poster submission is still open. If you have registered and want to present a poster, that is still an option. Also, the Rubin Data Academy is coming up in just a few weeks. That will be basically an intensive week of presentations like what you're going to hear today over a variety of topics. And there will be some co-working sessions each day as well, so you can work together on projects with like-minded delegates. So registration is still open. You can register right up until the time of the meeting if you're interested. So I encourage you to register for that and set aside that week of June 17 through 21 if you're interested. And then a couple of other notes. We do have translated versions of a lot of our DP0 tutorials that have been translated to Spanish. So do check that out if you're interested and share widely, of course. And a couple other upcoming meetings, LSST related. There's a Latin America meeting in La Serena, Chile, coming up in a couple of weeks, and then LSST at Europe in the Canary Islands coming up in September. Okay, so today, May 30th, we will talk about source injection. Next week will be our Q&A with staff and co-working breakout time. And then in 2 weeks, Aaron Meisner will demonstrate how to run a custom source detection pipeline. And of course, you can always go to dp0.lsst.io to see the schedule of upcoming events, a snippet of which is shown here. And I think that's all I had for announcements. I was hoping to play the video, but since I spilled my coffee everywhere, I will just encourage you to go check it out. There's a Rubin Observatory YouTube channel, and you can see the video of the camera's journey from SLAC to the mountaintop on our YouTube channel. Okay, so now we're going to go through tutorial notebook 14 today, so that when you first log into the science platform, you will see something that looks like this. You probably don't have nearly as many folders, but you should have one that is called notebooks. And within that, you should see the tutorial notebooks. And so we'll open notebook 14, which is, here we are, GP0214, injecting synthetic sources. That will be our subject for the day. Okay, so this is a little bit more advanced tutorial because it requires a little bit of knowledge about things like the butler and how to retrieve images and how to display images. It shows you a little bit of difference imaging, which you'll see at the end. So what we're doing here is we are going to inject some simulated stars and galaxies into an image, and then using the properties, the measured properties from that image to scale and process those stars and galaxies so that they match the properties of the image. And then we're going to show you how to take a template image of the same piece of sky, subtract that off, and verify that the injected sources look like we expect. So I'm gonna skip some of the text is here, so you can read through that on your own time if you're interested. But I will note here that the package, this is an internal LSST Science Pipelines package called source_injection. And this package can be used to inject sources into images from all the different stages of the pipeline processing. So you can, for example, inject into the post-ISR CCD images, which are the sort of the earliest processed images. We're going to inject into the CalX images, which are the calibrated exposures. So they've been calibrated to an excuse me, an external astrometric and photometric catalog. And you can inject directly into COAD images, deep COADs, if you want. And the method will look the same. The driver is slightly different, but you'll see an example of that a little bit later. And so the underlying framework that is generating the sources and the images of sources to inject is based on something called GalSim, which I will show you briefly. So this is the documentation. It is linked here. GalSim is just software to simulate objects, astronomical objects. It can do stars, of course, galaxies, parameterized in a whole bunch of different ways. You can apply, shear to the galaxies, all kinds of things. It's got a lot of options, and you can see in the documentation here, instructions on how to do a lot of those things. So GalSim underlies things. So anything that GalSim can do, I believe you can do with the source injection package. And if you want to know more about the source injection package, there's a link to the documentation for that on our Science Pipelines website. And it starts off showing you a nice example of a real image with some galaxies injected into it. So you can see without and with those galaxies injected. But there's a lot more documentation here about how to generate the catalogs, ingest them into the butler, inject the sources, and look at the outputs and everything. So there's a lot more detail here if you are intrigued by what you see today. So as usual, we start off by just importing all of the packages we need. We have some standard, AstroPy, NumPy, Matplotlib, and then a bunch of things from the LSST Science Pipelines We'll need to use the butler to access some data products. We'll use the AFW display to look at images. And we have the pieces from the source injection package that we'll need to ingest, to generate and then ingest injection catalogs and to actually do the injection. And then there's a difference imaging task that we'll use later on. So we'll go ahead and execute that. Okay, that was slow. Interesting. Okay, so the first thing we're going to do is we're going to get an image that we can inject sources into. So you've probably seen this before. We first instantiate a butler. If you want to know more about the butler, you can go to our tutorial notebooks 4, I think it is. Yeah. So after we've instantiated the butler, we will just do a little query that finds CalX images that overlap a particular tract on the sky. And so we will use this SQL-like query where we say we want the DP0.2 images. So that's specified by the instrument sky map. We want them to overlap this tract. You could specify a different tract if you wish. And I just arbitrarily chose detector number 19 because we just are going to get images from one single detector and in the G band. And so then you just pass that to this Butler query data sets where we ask it for a CalX and we say where these conditions are met. And you'll see here we'll print how many matches there were to the screen. And then we'll just arbitrarily pick the fifth one of those. You can pick whichever one you want by changing this index. And so you can see there are 23 images that that meet this condition. And I just picked one arbitrarily. It has this visit number and detector number 19 as we requested. So that's the image we're going to use throughout the notebook. And so then we just retrieve that from the Butler by using that data ID that we just picked out from that query. Excuse me. Okay, so we'll need to know a little bit more information about the image to be able to generate sources that overlap it on the sky. So mostly we need to know where in sky coordinates this image is. So we can use some of the methods that are associated with this CalX. So we can use this to get the WCS, the World Coordinate System, and the bounding box. The B box is the bounding box coordinates. And then we can use that WCS to convert those bounding box coordinates into sky coordinates. And so that's what this cell is doing. And so you can see the bounding box goes from 0 to 4,000 roughly. It's roughly 4,000 by 4,000 pixels. And then in sky coordinates, this is the sky coordinate of the center of that image in RA and DEC. And so then we can use that to tell the source injection tool where to put simulated objects. And then just to figure out, and we know it's 4,000 by 4,000 pixels roughly, we might want to know how large it is in degrees. And so you can use that WCS and that bounding box to actually figure that out here. And so you can see that the size of this image in degrees on the sky is about 0.2 degrees. And so we'll use that fact in just a second. So now that we've retrieved the image, we want to generate the catalog that we're going to inject into the image. So we'll use this generate injection catalog function to generate the sources. And we select a radius of about 0.1 degrees so that it should fit within this 0.2 degree rectangle that we have. So that's what this next cell does. And then we get to the fun part. So the simplest form of galaxy parameterized galaxy model in GalSim is the Sursic model, which is this is the flux profile of an object. And so you see you just have an exponential. If this n equals 1, then it's just an exponential profile, but n can take values larger than 1 as well. And so it's just, and then you have this effective radius, the half-light radius, and it's just specifying the flux profile as a function of radius. So we will specify that Sursic index n, which is the exponent, goes into the exponent here, and the half-light radius in the catalog. And we can also, if we want to create, this is a circular profile, but if we want to create elliptical profiles, you can specify the ratio of the minor to major axis. That's this Q that we'll use, and then you can rotate it as well. So you can specify a rotation angle beta. So we'll specify those as well. Now, this generate injection catalog method, if you give it, magnitude, a list of different Sursic indices, and all of the other parameters, it will basically do all the various combinations of those. So for example, here you can see what we're going to give it is a single magnitude, 3 different values for the Sursic index, 3 values for the minor to major axis ratio, and 2 values for the rotation, and 1 value for half-light radius. And so it will generate 1 times 3 times 3 times 2 times 1 different combinations of all of those. So we'll get 36 simulated galaxies back by doing this. And so it's just a way of sort of making it convenient to generate a large list. I'm going to execute this while I'm talking. Yeah, it makes it convenient to generate a large list with a variety of properties. But what we do here is we use the generate injection catalog function, and we tell it the limits in right ascension and declination. So remember, we specified that inject size above. So we say generate coordinates between these RA values and these dec values, and it will just randomly choose positions within that. If you don't specify this random number generator seed, then you'll get something that looks different than mine, or you could specify a different value here. This is included here just so that you can reproduce the results that you see in the tutorial. So if you wanted to generate, repeatedly different sets of galaxies, you would not want to explicitly specify the random number generator seed here. So we tell it we want Sursic source types, and then we give it, we're going to put them all in at the same magnitude. They're all going to be really bright 15th magnitude galaxies at a variety of Sursic indices, ellipticities, 2 different rotation angles, and then all with the same half-light radius. And this is in pixels. So they should have a half-light radius of 15 pixels. So you can see when I executed this, it did 18 combinations. Oh yeah, I misspoke before. The 1 times 3 times 3 times 2 times 1 gives you 18, but then the number equals 2 says do that same thing twice. So that's where we get to 36 sources. So that's how you generate galaxies. And then you can do the same thing to generate stars. And so you see here, we just say source type equals star. And in this case, we're just going to give it 5 magnitudes and say do that 7 times. So that should result in 35 stars. And that's all you have to do to generate stars at random positions within the RA dec ranges that you specified. And so there we go. We generated a catalog with 35 stars. So let's take a look at what those catalogs look like. So we'll just use this AstroPy VStack method to stack those two catalogs together, and then we'll take a look at it. Oops, sorry about that. There we go. So you can see we got the 36 galaxies and 35 stars. We have 71 objects. It assigns each object an ID. The RA and DEC, as I said, randomly positioned in the area that we chose. You can see the source type here. We have the Circe galaxies, and we have the stars, magnitude, and then all of the properties that we specified. And of course, for stars, you don't need a rotation angle or ellipticity or any of that. So those are just empty, and that's totally fine. Okay. Another thing you can do is actually take a postage stamp image and inject that into an image that's been processed by the LSAT science pipelines. So we're going to show you an example of that. And so this could be, for example, you ran a simulation and generated some simulated image, and you want to inject that into a data set with, you know, the real properties of that data set. Or in this case, we're going to take an image that comes from the NASA extragalactic database. Here's where that comes from. This is going to be an image of this object in GC 4152. You can go to the images tab here, and you can see you can download FITS images from various surveys and various in various filters. So we're going to use the one that comes from the Sloan Digital Sky Survey in the G band. So that's this image here. Excuse me. And here's another fun example. You can inject any image you want as long as it has a valid FITS WCS. That's the definition of a world coordinate system. Basically tells you the mapping from pixels to sky coordinates. And so, oh no, where did it go? It must be this one. No, we already saw that one. This one was the one I was going to show you. So you can inject the Rubin Observatory logo into an image if you want. So really, you can inject anything as long as you can define a WCS for it. Okay, so this image should be already come in your notebooks directory alongside the notebook. So we'll just open that and take a look at it so you can see what we're going to inject into the data, and you can see it's this pretty spiral galaxy. And now we're going to put that into that calyx image that we loaded before. So to do that, we're going to create another entry, one more line in that catalog that we have 71 sources in. We're just going to create another line for this object, and we're going to put it at some right ascension and declination. We're going to give it an ID of 9999, and we're going to assign a magnitude. And then here you can see we say source type stamp instead of star or Circe as we used before. And then you just give it the file name of that file that we downloaded from NED. And so this specifies an AstroPy, or makes an AstroPy table with one line in it, and then we use that VStack method again to add this line to the end of that table. And you can see now the bottom line has that 9999, and you see over here the stamp file name. Okay, so now we have our catalog that we want to ingest into the Butler and then tell it to actually inject these sources into the data. You are all welcome to pop in with questions at any time, of course, but I'll pause here just to see if there were any questions before we move on. Yeah.
Hey, Jeff. Thanks. I actually have several quick questions. So when you create a catalog, the randomness part is only the R deck, right? Like all the other parameters, it would just do all the combination. It's not sampling from the other parameters.
That's right. Yeah. There, I believe there is also a method that you can specify a range and it will generate
Okay,
a random list if you've specified a range of magnitudes, for example.
right. And then for the postage stamp, you mentioned that the header need to have a word coordinate. But then you also specify RN deck. So what does it actually do? It take the original RN deck and then rotate into the new RN deck that you specified, or
Yeah, exactly. So really, it just needs to know the essentially the pixel scale, and yeah, so it just reprojects it into the RA deck that you give it.
I see.
And
But keep like for example, keep the rotation. Like I cannot take an image, rotate it, and then putting into.
I think you would need to do that rotation, change the WCS of the stamp before injecting it to do that rotation.
I see. Cool. Thanks so much.
Oh, you bet. Yeah, Alma.
Yes, sorry if I missed it, but it's related to what Jao was asking. So for the case of postage stamps, you mentioned we have to have the word coordinate system in the file. But to do the rotation, the beta parameter in the catalog could also work for doing the rotation, or as you were saying, we have to rotate the postage stamp itself before injection.
Yeah, unfortunately for the postage stamps, yeah, that beta parameter will not work for the stamps, because that's a GalSim parameter, and as far as I can tell, GalSim doesn't have a way of rotating the stamp itself. So you would need to rotate the stamp, and basically change its WCS to make that work.
Okay, thank you.
Sure.
Hey, Jeff.
Hey, Ori.
I can't actually find the hand raise button for some reason, but very basic question. I missed the first few demos earlier on. Going back to selecting your track, how is that? What's the easiest way to figure out what track you actually want to do? Do you recommend using what do you call it? The interactive platform aspect of this?
Yeah, the portal is
Portal, yeah.
sort of the easiest way of doing that, because you can kind of interactively, poke around and figure out what you want. There are, I'm trying to think of which of our notebooks we do that in. There are ways to get fairly simple ways to get, if you know, say, the RA and deck coordinate that you're interested in, to figure out which track that overlaps. And so I can't recall exactly which of our notebooks do that, but it's fairly simple. You can get the sky map object, and you can sort of use some of the methods that are associated with that to figure that out.
Okay.
I'm tempted to try and live demo that, but I know that I would fail.
But there is a notebook, yeah.
Yeah, and
Okay.
it'll probably pop into my head at some point here, and I'll remind you. But yeah, we do demonstrate that somewhere in our notebooks.
Okay, very good. Thanks.
Let's see, where were we? Yeah, okay, we generated our catalog. Excellent. Oops. Okay, so the next thing you need to do is take that catalog that we generated and ingest it into a collection in the Butler, so that then the Butler, we can use pipeline tools to actually generate and inject these sources into the image. So I will note also, I forgot to mention that you don't have to use that generate injection catalog method to create this. You could just manually create or programmatically create this same table as long as it has the right columns that are expected. So for example, in the delegate contributions notebooks, there's a demonstration of injecting variable sources into images where we just generate a sinusoidal variable that looks like, I'll show you what it looks like. There's the magnitude as a function of time. And where's the catalog? And just generate a catalog like this, and you can ingest that into the butler. So you don't have to use that generate injection catalog method to do this. Okay, so the first thing you need to do, this cell will get your username and then use it to create a collection that has your username and then test injection inputs. And you'll see a note here that if you try and inject into a collection that already exists, it will complain and say that collection already exists. I'm not going to do anything. So this is an unfortunate bit right now that if you've run this before, you'll see that complaint. So I'm just going to, I don't know, here we'll put today's date at the end of the collection name because I have run this before. But what you do then is you just give a name for the collection that you want to put things into, and then you instantiate a butler that where you say writable equals true, because we want to be able to put things into the butler. So we do that, and then we use this ingest injection catalog function. This basically takes as its inputs pointer to that butler, that writable butler that we just instantiated, the table that we created. You need to tell it which band you want to inject into. So we put G band in the catalog, so we'll use band equals G here. And then that collection name that we specified before. Actually, here, I'll show you what happens if you try and inject into a collection that you've used before. You will see a message like this that says, I found an existing collection with that name. So if you see this, your catalog was not ingested. So what you can do then is specify a different name for your output collection. And now when I run it, you see success. We ingested that one catalog. So now that catalog is in our butler, we can use these tools to actually inject those sources. So we need some information about the image. We need to know about its point spread function, its WCS, and the photometric calibration object, so that it knows how to convert from the specified magnitudes to flux in the image. So we grab all of those from that CalX image that we retrieved earlier. And then we are ready to load that catalog that we ingested into the butler. We're just going to go and load those back from the butler. So this is how you do that using the butler registry query datasets method. Excuse me. You say, I want the injection catalogs in the G band from that collection that we specified before. And then after you retrieve those using this query, you just can loop over all of them, because you'll see it actually put them in two different trixels, spatial shards on the sky. So that's the reason you need this method, is there are actually two catalogs when you do this query and retrieve. So this just retrieves those. And then we'll pass those to the task. Okay, so now's the fun part, which you may have seen in some of our other tutorials, where to run methods from pipelines, you will need to usually instantiate the config class for each one, which allows you to modify and specify different configuration values that change how the task can run. And then you instantiate the task, and then you can actually run the task subsequently. So we'll do those steps next. Just a side note here that if you instead of injecting into a CalExp, which will use this visit inject task, if instead you wanted to inject into a coad image, for example, you would use the coad inject task and config. And there's a little bit of explanation here about the differences between those tasks. So to instantiate that config, you just specify it like this, and then we set the prefix telling it where to retrieve that stamp image from. And that's the only thing that we need to customize. And then we can instantiate the visit inject task, feeding it this configuration that we have instantiated and modified. And I can show you what that configuration looks like, actually, just in case you are curious. So this has a whole bunch of things that you could modify if you wanted. So this tells it, what columns to use to retrieve RA and DEC, for example, what radius to use to calibrate the fluxes, all kinds of things like that. So that just shows you what that object we retrieved looks like. But now let's get to the fun part where we actually run the visit inject task. So we called it inject_task here. And you'll see, actually, I'll show you that too. Oops. You can see all of the methods that task, sorry, show you what I did here. Just use this standard Python method to see what tasks or what methods it has associated with it. And in this case, you can see it has, you can look at its configuration. You can get the task name or various other things, but what we want is the run method. That's what we're gonna actually execute to inject sources. And the run method takes a few inputs. You need the injection catalog. You need the image, the CalExp. And as I said before, you need the PSF, the WCS, and the photometric calibration info. And so we already retrieved all of these things. And then you will get back from this method the output exposure that has the sources injected and an output injection catalog, which should be identical to the original catalog, except it will also include the XY coordinates that were generated from the RA DEC coordinates. And one thing I will note here too is that if you just gave it the original CalExp that we retrieved, it would actually inject the sources in place. So it would essentially overwrite that CalExp with the new one. So we actually feed it a clone of the original CalExp so that we can compare the two after the fact. So here's how you execute that run method. You say inject task.run. We give it the injection catalogs that we retrieved from the butler. We give it the CalExp and we tell it to clone it so that we're not overwriting it. We give it the PSF, the photocalib object, and the WCS. And then after we execute it. So this runs it, and then this just retrieves the two objects from the injected output. So you retrieve the exposure and the catalog. And so this might take a minute, but you'll see it'll inform you what it's doing as it goes along. In some cases here, we apparently specified some one source that is outside the bounding box of the image. So it won't even, it identifies that and says, I'm not going to bother with that. But then it says, I'm going to generate the other 71 sources. And you can see it's still chugging away here. And yeah.
While we're waiting, so
Mhm.
when we generate a table, didn't we specify everything should be within the bounding box? So why one of it is outside?
We didn't exactly. We did a very rough. It's a good question. We did a very rough. We just set the RA deck boundaries,
Right.
And so I guess with that, what was it, 0.1 degree radius, and so yeah, I think one could do something more careful and ensure, check before continuing that that they all would land in the bounding box. But I think because we just specified a radius, it generated one right at the edge and happened to miss.
Yeah, and I have some question about this now no overlap and Fourier transform size error. Maybe I don't know if you're planning to talk about that.
Oh yeah. Yeah, you can see some of these warnings that you get, and some sources that were skipped. So there's the one that didn't overlap the image, and the FFT size error. I honestly don't recall exactly what that is, but my guess is it's saying if you specify an object that is that right? I think if you specify an object that's going to end up being really huge, it says that's what these clipping things are as well. It says like, whoa, I don't want to spend all of the energy to put in something so big. And I think that's like, you could configure that if you really wanted to put it in something bigger than 10,000 pixels. But that's what these are. But the FFT size error, I think, may be related to that as well, but I'm not sure. It's a good question. I should look into that.
Is there a way to know which ones that are not injected? Because now it says that injected 63 only. So can we figure out, is it possible to figure out which ones are not being injected?
Yes, yeah, even in the message here, it actually tells you that these are the actual flags that are set in the catalog. So you can go and check exactly which ones were missed. And since we're kind of short on time, I won't try and go and look at those right now, but you could. Yeah, Ori.
Hey, Jeff. I got to run in a second. Thanks. This is great. My big question is if you ended up wanting to use some sort of other simulator. So I guess maybe I know you said it's possible, right? If you created your own simulations, right?
Mm-hmm.
Where do the Gaussian, so the inject source, the Gaussian, I'll have to review this notebook, but the Gaussian sources are created before the inject method. Is that correct or not? So I'm just trying to I'm trying to understand where in this process, if I've created my own, PSF and I want to inject that, where does that come in? Where does that happen?
That would be, yeah, actually. So that's a good question, because in this case, you can see it tells you here actually when we said source type equals star, it actually uses the delta function method from Gaussian. But I think so then if you generate, or if you specified a different PSF, like an actual PSF object as an input here, I think that would be a way of doing that. Otherwise, you could just create like a stamp image that is some arbitrary PSF and specify that as a stamp. But here it actually, it doesn't create the objects until you execute the inject task. And it uses, the parameterized ones. It uses all the parameters we gave it. But for the stamps, you could do all of that beforehand if you wanted.
I see. And it says in the documentation, it says the PSF is retrieved from the exposure. So is that PSF like in some like repository, like for each exposure you have some sort of like empirical PSF that's been calculated for that field, for that stack? Is that what's going on?
Yeah, you have the actually I think that should work. Yeah, so the image object that we retrieved is an object that has a bunch of other information that comes with it. So the PSF, for example, is this. We use PSFX to measure and save our PSFs. So this actually is the PSF object that comes with that particular image. So you could, I think that it's interesting what you were just saying about the documentation, because I think it uses, if you specified a different PSF, like this PSF that we gave it is actually the one from that CalX, but if I gave it a different PSF, as long as it was parameterized properly, it was a PSFX object, then it should be able to use that.
Awesome. Yeah, I might experiment with it. So that's great. Cool.
Cool, thanks. Okay, I'm going slower than I expected, but the next thing we're going to do is this ran and it says, oh yeah, I injected 63 of the 71 sources. And so I don't know, first thing I wanted to do was just look at the original image and the new image. And so that's what the next cell does. This was the image that we originally retrieved. And now you can see all of our funny looking galaxies. And you can maybe tell that there are stars that aren't in this image that are in this one. So, oh, and I can also point out that that stamp image is here. So there is one line in here that you can uncomment, and it'll zoom in on the coordinates of that stamp. And then you can see that spiral galaxy injected into the image. Okay, so the last thing, I'm just going to breeze through this quickly because we're nearly out of time, but the last thing we do here is we show you how to retrieve a template image that comes from a coad of the images that had the best seeing, that then can be used as a template to subtract off of this injected image and see what is left. So we're just going to execute the difference imaging really quickly. So we retrieve that template exposure using the same data ID that we used for the CalX that we retrieved earlier. And then we're going to run this task, this Allard lepton subtract task. That's the image differencing task. And it will give us back some resulting image. And it'll tell you lots of fun stuff along the way. And you can see it's convolving. It checks out the PSFs of the two images and then convolves them to match the PSFs of the images and other such fun. And then the last thing we do is just compare the original image and the difference image so that you can see that it successfully injected all of the sources that we told it to. And so this will take just a minute to run. And it should show us, oh no, my kernel was almost running out of memory. Okay, and then it displays, this is the template image, and then this was the image that we injected synthetic sources into. And so you take this middle image subtract the template image, properly scaled, of course. And then this is what remains. And so you can see the galaxies that we specified, as well as a few of the stars that we asked it to inject. And so this is a really basic introduction to how the task works. You can specify all kinds of different types of sources and different parameters for them. And so I encourage you to explore if you are interested. And I'll also note that there, in addition to the variable star injection notebook that's in the delegate contributions, there is also one that shows you how to take the calyx that you injected into that have different rotation angles on the sky, and actually warp them all so that they are at the same rotation. So do check those out if you're interested as well. And we have just a few minutes left if there are any other questions anyone had. Thanks. Tobias.
Hey, thanks for this. This was very useful. I had one question about the ingesting of the injection catalogs. So if I understand correctly, like you're saving the catalog somewhere, like in the Butler, right? And so presumably, like what I want to do, I want to inject a bunch of sources. And so I'm afraid that I just keep saving like data somewhere. So I was wondering, like, is there a way to like remove the whatever catalog that you saved? Or is this something I should be worried about, or can I just keep saving stuff somewhere?
No, it's a good question, and there is a way, and we kind of are shy away a little bit from showing people how to remove things from the Butler, just because it's a shared Butler, and so potentially if you did something wrong, you could remove everything or anything, but there are definitely ways, and I would be happy to show you how to delete things from the Butler. But in general, I would say don't worry about it unless we're talking like mega volume.
Okay. Yeah.
But it certainly can be done, and there is in fact you can also search the community forum and find instructions on how to do that.
Awesome. Okay, thank you.
Sure. Any other questions, comments?
If nobody else has another, I had one more small question that I was wondering if we could access those notebooks that you said that were the delegate contributions.
Oh yeah, I'll show you where those live.
Yeah, thank you.
Yeah, thank you for asking. I should have showed you. So we have this here, I'll paste this into the chat. In our GitHub organization, this Rubin DP0 GitHub organization, you can see there's a delegate contributions DP02 here. And you are all encouraged to contribute, by the way. If there's some exploration you did, you are welcome and encouraged to share it here. And so this, I clicked into that, and you can see here, where did it go? There's a folder called Source Injection that has those two notebooks, the one that shows you how to align the calyx that are at different rotation angles, and the one that shows you how to inject variable objects, essentially at simulating a variable star and then choosing the right magnitude at each calyx to inject it into.
Awesome. This is great. Thank you.
Sure. Yeah, and you can see also in this delegate contributions, we do have quite a few contributions, and there's at the bottom here, I guess this doesn't have a directory or summary, but there are lots of things. So this is a great resource for more extended explorations. Okay, we're about at the hour. Any more quick questions before we wrap up? All right. Well, I will remind you all that next week we have our drop-in Q&A co-work time. If you want to explore source injection more, for example, feel free to pop in next week, same time, same Zoom room. And thank you all so much for attending. Hopefully I'll see you at future events.
Nice work, Jeff.
Thanks, Bob.
Thank you.